At noon, a luxury plaza in Dubai appears to have defeated the desert. Behind the glass, temperature and humidity are controlled, while the pavement outside radiates heat. Empower reports more than 1.66 million refrigeration tons of connected capacity across its Dubai network. But cold is not created by destroying heat. It is created by moving heat. ASHRAE's traditional benchmark exposes the hidden arithmetic. A system removing 12,000 BTU per hour as one refrigeration ton may need to reject about 15,000 after compressor work is added, although modern equipment can narrow that gap. So every protected bubble has another side: a condenser, a cooling tower, an electrical demand, and a place where the heat is released. The customer buys the cold. The outside world receives the thermal invoice. Dubai may have industrialized comfort, but what if the machinery protecting its most valuable spaces is quietly adding pressure beyond their walls? The answer begins behind a mechanical door almost no visitor sees. Before following that heat into the machinery, look at what Dubai has accomplished. Thermal comfort is no longer a device attached to one room. It has become urban infrastructure. Central plants circulate chilled water through buried networks, serving dense commercial and residential districts. Empower says district cooling can use up to 50% less electricity than conventional cooling. That efficiency helps malls, hotels, offices, residences, and transport-linked developments remain usable through the harshest months. Dubai did not merely install air conditioning. It industrialized escape from summer, but the achievement contains a division hidden in plain sight. Inside the boundary, air is cooled, dried, and filtered. Commercial life continues almost untouched by the weather. Outside it, pedestrians still face solar radiation, hot paving, reflected glare, and humid air. The network does not create one shared climate. It creates protected islands, separated by exposed routes. Dubai did not abolish summer. It placed summer outside the door, then turned relief from it into a service delivered through property, transport, and access. Is this a city cooling itself, or becoming better at shielding selected spaces from the heat surrounding them? The glass door is only the border. The transaction begins behind it. To expose that transaction, follow one packet of heat out of the protected space. At the evaporator, refrigerant absorbs thermal energy from indoor air, or a chilled water loop. The vapor enters the compressor, where electrical work raises its pressure, before moving toward the condenser. This is the part the luxury surface never shows. ASHRAE explains that the condenser must reject both the heat removed at the evaporator and the heat of compression. In its traditional cooling tower definition, one refrigeration ton removes 12,000 BTU per hour, while the tower may be sized to reject 15,000. Modern equipment can narrow that difference, but no machine can erase the rule. The heat must leave. In an air-cooled system, an outdoor coil transfers it to surrounding air. In a water-cooled plant, the condenser transfers it into condenser water, and a cooling tower releases that load to the atmosphere, partly through evaporation. The outlet may sit on a roof, inside a plant yard, or high above the public realm. It does not need to blow directly onto the pavement to remain part of the outdoor heat balance. A blue stream disappears from the protected interior. A larger red load emerges carrying the original heat plus the energy used to move it. The machine does not kill heat. It changes its address. This is the hidden invoice behind artificial comfort. The customer keeps the cold, while the removed heat and compressor work are released beyond the protected boundary. Would the plaza still feel like a miracle if that invisible transfer were painted across the skyline? One machine doing this is refrigeration. Thousands operating across the same district become a climate question. Now expand the frame. One condenser becomes hundreds. One cooling plant becomes a network. One protected lobby becomes an entire district built around the promise of continuous cold. Air conditioning is not the sole cause of Dubai's urban heat island. Solar radiation, asphalt, concrete, glass, traffic, vegetation, humidity, building geometry, and wind all shape outdoor temperature. But mechanical cooling operates inside that system. A Dubai study examined 5 years of hourly weather data from 2014 through 2018 across 3 monitoring stations. The researchers found that the urban temperature contrast changed sharply with wind speed and direction. Rejected heat is easiest to disperse when the atmosphere is willing to carry it away. Under weaker ventilation, the city becomes less forgiving. Hot surfaces warm the air. Buildings demand more cooling. Compressors and pumps operate longer. Condensers and cooling towers reject more heat. That load joins traffic, solar gain, and heat stored in the built environment. The result is not one machine heating an entire neighborhood by itself. It is a feedback risk created by thousands of machines operating inside the same stressed thermal system. A building may remove heat from its interior, but the district must still absorb, transport, or disperse what emerges from the other side. The problem is no longer that one tower rejects heat. The problem begins when an entire district depends on the assumption that the atmosphere will always carry that heat away fast enough. Thousands of cooling systems are no longer merely fighting the urban climate. Under the wrong conditions, they become participants in it. And the most dangerous heat may not be what Dubai releases beneath the afternoon sun. It may be what the city fails to lose after dark. During the day, Dubai's surfaces absorb an extraordinary thermal load. In the 5-year station study, one monitored location recorded an air temperature above 50 degrees Celsius. That number does not describe every street, but it reveals the environment the city's cooling systems are built to resist. Glass receives solar radiation. Asphalt and concrete store it. Vehicles add heat at street level. Buildings remove energy from their interiors and reject it beyond the protected boundary. Then the sun sets. The sky darkens, but the thermal cycle continues. Roads, walls, roofs, and parking areas release energy stored during the day. Buildings remain occupied. Hotels, apartments, malls, and offices continue demanding cooling. Pumps move chilled water. Heat rejection continues, while the urban fabric is still trying to cool. This effect is not identical across Dubai. Wind speed, wind direction, humidity, atmospheric stability, and street geometry can weaken or intensify it. A district with open airflow may release heat efficiently. A dense corridor under weaker wind may hold part of the burden close to the buildings that produced it. Through a thermal camera after midnight, the interior may appear blue, while nearby roofs and paving remain orange and red. During the day, Dubai absorbs heat. At night, it attempts to breathe that heat back out. But before every surface has cooled, the next sunrise begins loading the city again. Dubai is no longer fighting only today's heat. It may be using tomorrow's electricity to pay a thermal debt carried forward from yesterday. Once that debt enters the next cooling cycle, the problem leaves the atmosphere and enters the infrastructure balance sheet. Higher cooling demand does not remain a temperature problem for long. It becomes a construction program. More demand requires larger plants, more pumps, more insulated pipe, more electrical capacity, more water management, more maintenance, and backup systems designed to keep the cold moving without interruption. The scale is already enormous. Empower lists 90 district cooling plants serving 1,747 buildings and more than 156,000 customers. Its connected capacity exceeds 1.66 million refrigeration tons, with reported availability above 99.9%. Those figures do not prove district cooling is failing. They prove how deeply continuous cooling has been built into Dubai's physical operation. District cooling can use substantially less electricity per refrigeration ton than conventional systems. But efficiency per unit does not end the dependency if total cooled floor area keeps expanding. One efficient plant connects another tower. That tower attracts residents, offices, hotels, and retail. Those buildings create a permanent expectation of controlled temperature. The expectation supports leases, property values, tourism, and year-round commercial activity. Reducing cooling is no longer a simple energy decision. It threatens the economic assumptions built around the network. This is the second feedback loop. Heat drives cooling demand. Cooling demand drives infrastructure. Infrastructure enables more development. More development creates a larger baseline demand that the city cannot easily remove. Dubai is no longer cooling individual buildings. It is expanding an urban economy whose normal operation increasingly depends on industrial refrigeration remaining available almost every hour of the year. The thermal invoice has become infrastructure debt, and infrastructure debt can remain invisible underground. The next bill cannot. It is written directly onto the human body. The human cost of Dubai's heat is serious enough to appear in national labor policy. In 2026, the United Arab Emirates again prohibited work in open areas and under direct sunlight from June 15th to September 15th, between 12:30 and 3 in the afternoon. That rule does not prove cooling systems created the danger. It proves outdoor heat exposure is a recognized occupational risk. Inside Dubai's cooled network, hotel guests, office workers, residents, and shoppers can move between air-conditioned vehicles, enclosed lobbies, elevators, and protected interiors. Outside it, delivery riders, security personnel, landscapers, maintenance crews, construction workers, and pedestrians cross the spaces between those bubbles. Follow one delivery rider during the afternoon. He waits outside a cooled commercial complex. The automatic door opens, and cold air reaches his face. He steps inside, collects a package, then returns to humidity, reflected glare, and paving that has stored hours of solar energy. His uniform traps heat against his body. Sweat becomes less effective as humidity rises. He crosses an exposed route, passes a loading area, and waits beside the service side of the development engineered to protect the customer. The scene does not require a condenser to blow directly onto him. The inequality already exists. One person remains inside the protected climate. Another repeatedly leaves it to keep that climate supplied, cleaned, guarded, repaired, and connected to the city. The customer receives the cold. The worker crosses the heat between cold destinations. The benefits of artificial comfort and the burden of outdoor exposure are distributed through income, occupation, transportation, shade, and building access. Urban heat is no longer only an engineering problem. It becomes a class system measured in degrees, distance, and doors. And the final humiliation is that Dubai once possessed a cheaper way to protect the public realm, before the city became dependent on machines to rescue each interior separately. The deepest humiliation is not hidden inside a chiller plant. It is preserved in the streets Dubai once knew how to build. Traditional districts in the Emirates were never naturally cold, and they could not produce modern indoor temperatures during the most severe summer weather. But they attacked the heat before it entered the building. Narrow routes reduced direct solar exposure. Taller walls cast longer shadows. Courtyards created protected internal space. Wind towers and carefully placed openings supported air movement. Compact geometry shortened the distance people had to cross beneath the sun. A peer-reviewed study compared 3 traditional and 3 modern residential sites in the United Arab Emirates. Its conclusion was not that the past offered perfect comfort. It was that urban form and density changed air temperature and human thermal comfort before mechanical cooling even began. That distinction is devastating. The old strategy tried to reduce the thermal load shared by the street. The modern strategy often allows roads, paving, glass, and open space to absorb the load, then rescues selected interiors after the heat has already arrived. Dubai's own building rules now recognize the same problem. They set solar reflectance thresholds for roofs and contain specific provisions addressing hardscape heat island effects, microclimate, and outdoor comfort. These are not rules written by a city that believes more cold air alone can solve outdoor heat. They are an admission that surfaces, shade, material choice, and pedestrian exposure matter. Dubai did not simply replace old buildings. Across many modern districts, it replaced a public defense against heat with a private defense inside property lines. The city of the future may be losing a thermodynamic argument against the city it replaced. And rebuilding that lost protection is far more difficult than installing another machine. At first, the escape appears obvious. Build more efficient plants. Store cold water when demand is lower. Upgrade controls. Recycle more water. Use smarter forecasting to move cooling production away from the most stressed hours. Dubai is already moving in that direction. Its energy strategy has targeted district cooling penetration of about 40% by 2030. Building regulations have required new district cooling plants to include thermal energy storage equal to at least 20% of design capacity. These measures can reduce peak demand and improve efficiency. But they also reveal how deeply the city expects industrial cooling to remain embedded in its future. Every efficiency gain protects the existing model. It allows another hotel, tower, mall, and enclosed attraction to be marketed on the promise that outdoor conditions will never interrupt indoor life. That creates the first trap. More efficient cooling reduces the cost of each unit, but lower cost can support more total cooled space. If demand grows faster than efficiency improves, the dependency still expands. The second trap appears if Dubai tries to reduce cooling. Hotels lose usable hours. Offices and homes become harder to operate. Retail traffic weakens. Vulnerable residents face greater risk. Property values built around guaranteed comfort come under pressure. The third trap is urban redesign. Dubai can add shade, reflective roofs, cooler paving, better envelopes, vegetation, and protected pedestrian links. Its own green building system already requires several of these measures in new construction. But a new rule can change tomorrow's project more easily than yesterday's district. Existing roads remain wide. Towers remain separated by exposed routes. Parking areas, facades, utilities, and land values have already been fixed into place. Retrofitting them demands years of construction, capital, traffic disruption, and negotiation between thousands of owners. Extreme heat does not pause during the retrofit. The trap is not that Dubai has no solutions. The trap is that the fastest solution deepens the mechanical system, while the least mechanical solution requires surgery on the city itself. Dubai no longer chooses whether it will depend on cooling. It chooses how permanent, expensive, and spatially unequal that dependency will become. When a system becomes impossible to abandon, it stops being a convenience. It becomes life support. That phrase sounds exaggerated until the meaning of failure changes. This is not a prediction that Dubai's electricity grid or district cooling networks are about to collapse. The systems are designed, monitored, maintained, and expanded precisely to prevent that outcome. The vulnerability lies in what an interruption would now mean. At the beginning of Dubai's growth, air conditioning was marketed as comfort. Then it became a competitive advantage. Today it supports residential safety, building operation, tourism, retail, offices, transport spaces, and the value of property designed for year-round use. Under extreme summer conditions, all of those demands rise together. Chillers operate longer. Pumps move more water. Condensers and cooling towers reject more heat. Electricity demand climbs while the public realm remains difficult to cross without shade, a vehicle, or another cooled destination. A failure in one building is local. A prolonged interruption across several buildings, one plant, or one district becomes a business and health emergency. Guests cannot simply accept a warmer hotel room. Offices cannot treat controlled temperature as optional. Residents in sealed glass towers cannot solve the problem by opening a window. Retail, food storage, elevators, ventilation, and digital equipment all depend on buildings continuing to operate within designed conditions. Dubai is not connected by one single cooling network. It is connected by one shared assumption. The cold will always be available. That assumption links separate plants, building systems, electricity supply, water management, maintenance crews, property contracts, and customer expectations into one economic promise. The more reliable the system becomes, the more completely the city is built around its reliability. More capacity protects the promise but deepens dependence. Less cooling reduces demand but immediately transfers risk to people and businesses. Urban redesign attacks the cause but moves too slowly to replace the machinery during the transition. Every exit remains open in theory. Every exit becomes painful in practice. The machine that began as an amenity now protects the operating conditions of the city itself. That is the final escalation. Dubai's cooling systems do not need to fail to expose the vulnerability. They only need to become so essential that failure is no longer tolerable. This is where the original promise collapses, not because the machines stop working, but because they must never be allowed to stop. Return to the plaza from the beginning. A visitor crosses the glass door and disappears into controlled air. This time, do not follow the visitor. Follow the heat. It leaves the protected space through the evaporator. It moves through refrigerant or chilled water. Electrical work drives the compressor and pumps. The combined load reaches a condenser, a cooling tower, or another heat rejection system. Then it returns to the environment beyond the boundary that the customer just crossed. Pull back. The interior remains cool. The machinery continues operating. The worker outside continues moving between buildings through the heat the city has not eliminated. Artificial microclimates are not useless. They protect health, keep homes and businesses functional, and make modern urban life possible during severe weather. That is exactly why the dependency is so difficult to question. Dubai has proven that capital and engineering can manufacture winter inside glass. It has not proven that multiplying those interiors creates a cooler city between them. The heat never disappeared. It changed location, passed through machinery, absorbed the energy required to move it, and returned outside the protected space. Only the person forced to experience it changed. Would you rather live in a city filled with perfectly cooled buildings, or in one designed so that stepping outside does not feel like leaving life support? Share your answer below. If this investigation changed how you see the machinery behind urban comfort, subscribe for the next hidden system shaping the modern city. This documentary examines thermodynamic principles, urban climate research, building regulations, and industry reporting. Local effects vary with equipment, weather, airflow, urban form, and operating conditions. It does not predict an imminent failure of Dubai's power or cooling infrastructure.